Hello, in this lecture we'll answer two questions. The first question, we find out the size of this angle x, and in the second question, we find out the area of this ring shape. So we start with the first question. In the drawing we have a quarter circle, AOB is a quarter circle. This is the angle AOB, this is the right angle. This is the angle APQ, this is also a right angle. In addition, we know that AP equals to PQ, and our task is to find out the size of this angle PQB is equals to x. We have to find out the value of x, the value of angle x. So first of all, we complete the quarter circle to a semicircle. And we define this point as point M. So actually, AM is the diameter of this semicircle according to construction. So write it down, AM is the diameter of the semicircle. AM is the diameter, it is absolutely a straight line. So if you focus on the right side of the straight line, AM is point O, here the sum of the angles must be equal to 180 degrees according to rule 3 that says that the sum of the angles on one side of a straight line is equal to 180 degrees. So which angles we have at the right side of AM is point O, we have this angle that is the right angle, plus this missing angle, in total the sum of those two angles must be equal to 180 degrees according to rule 3. Therefore this missing angle must be equal to 90 degrees in its size. In the next step, we will extend line segment PQ by straight line until it touches the semicircle. But the question is where the extended line segment PQ will touch the semicircle. We will assume that the extended line segment PQ will touch the semicircle at this point, point L. Repeat again, according to our assumption, the extended line segment PQ will touch the semicircle at this point, point L. And therefore, we have according to our assumption, we have peripheral angle APL. This is peripheral angle APL. And peripheral angle APL subtend on chord AL. Again, peripheral angle APL subtend on chord AL. The problem is that chord AL cannot be the diameter of the semicircle because it doesn't pass from point O, that is the center of the semicircle. And we know that only a chord that passes through the center of the circle or semicircle could be the diameter of the circle or semicircle. And because of the fact that AL doesn't pass through the center of the semicircle, it cannot be the diameter of the semicircle, and it is a contradiction to rule 5. So we click on rule 5. According to rule 5, any peripheral angle that is equal to 90 degrees must pass, again, any peripheral angle that is equal to 90 degrees must subtend on the diameter of the circle. So in the drawing, we have a circle. This is peripheral angle AOB that is equal to 90 degrees in its size, and therefore peripheral angle AOB must pass on the diameter of the circle, and indeed AB is the diameter of the circle. So here we have, now drawing, we have peripheral angle APL that is equal to 90 degrees in its size, and therefore according to rule 5 it must pass on it must subtend on the diameter of the semicircle. But actually peripheral angle APL subtend on AL, that is definitely not the diameter of the semicircle. Therefore we have contradiction to rule 5. So it is impossible that the extended diameter PQ will touch the semicircle at point L, because we have contradiction to rule 5. So in the next step, we will assume that the extended 97 PQ will touch the semicircle and will touch the circle at this point H. So according to our assumption, we have here peripheral angle APH that is equal to 90 degrees in size according to what is given as the equation, and peripheral angle APH subtend on chord AH. Again, we have contradiction to rule 5, because AH is definitely not the diameter of the semicircle, because it doesn't pass through point O, that is the center of the semicircle. And therefore, due to the contradiction to rule 5, we will derive from this that the extended 97 PQ will not touch the circle at point H. So the extended 97 PQ will not touch the circle at point L, and it will not touch the circle at point H. So we have to conclude that the extended 97 PQ will touch the semicircle at point M and not in any other point. So now we don't have contradiction to rule 5 anymore, because we have peripheral angle APM that is equal to 90 degrees inside, and indeed it subtends on AM, that is the diameter of the semicircle, exactly according to rule 5. So in the next step, we will join points A and Q together by a straight line. By joining points A and Q, we created the right and associated triangle, triangle APQ. Triangle APQ is right triangle because angle APQ is right angle, and triangle APQ is an associated triangle because side AP equals to side PQ. And we have the rule that in front of equal sides in the triangle, there are equal angles. So if you relate to the right and associated triangle, triangle APQ, in front of those two equal sides, we have those two angles that must be also equal to each other in their sizes. So if you define the size of this angle as alpha, then the size of this angle must be also equal to alpha because they are equal to each other. And we have the rule that says that the sum of the angles in any triangle is equal to 180 degrees. So which angles we have in the right and associated triangle, triangle APQ? We have this angle that is the right angle. Alpha plus alpha is 2 alpha, so 90 degrees plus 2 alpha must be equal to 180 degrees according to the rule that I mentioned. Here we subtract 90 degrees from this equation, and we get that 2 alpha equals to 180 degrees minus 90 degrees is 90 degrees. 2 alpha equals to 90 degrees. Here we divide this equation by 2, and finally we get that the missing angle alpha equals to 90 degrees over 2, that is 45 degrees. This is the missing angle alpha is equal to 45 degrees in size. And this is also the missing angle alpha that is equal to 45 degrees in size. In the next step, we will prove that those two right triangles can go into each other according to side angle side rule. That is to say, we will prove that the right upper triangle AOQ can go into the right lower triangle OQM. So, one those two right triangles can go into each other. We prove that the right upper triangle AOQ can go into the right lower triangle OQM. So why those two right triangles can go into each other? First of all, side AO of the right triangle AOQ equals to side OM of the right triangle OMQ. They're both the radii of the semicircle, therefore they're equal to each other. So AO equals to OM. If we define the radius of this semicircle as R, then AO equals to R and OM also equals to R. So I repeat again. Side AO of the right triangle AOQ equals to side OM of the right lower triangle OQM. Why? Because they're both the radii of the semicircle and therefore they're equal to each other. Each of them is equal to R. Unit in itself. In the next step, we have also those two angles, they are both right angles and therefore they are equal to each other. So clearly this is angle AOQ in the right triangle AOQ, and it is equal to this angle, this is actually angle OQM in the right triangle OMQ. So repeat again, and we found out that angle AOQ in the upper right triangle equals to angle OQM in the right lower triangle OQM. They are both equal to 90 degrees and therefore they are equal to each other. And finally, this is side OQ, that is a common side that belongs to both triangles. So we can write down that OQ equals to itself as a common side that belongs to both triangles. OQ equals to itself as a common side that belongs to both triangles. So we actually prove that the right upper triangle AOQ congruent, this is the sign of congruent, to the right lower triangle OQM according to side angle side rule. That is to say, we actually prove that those two sides and the angle that is included between those two sides in the right upper triangle AOQ are correspondingly equal to those two sides and the angle that is included between those two sides in the right lower triangle OQM. And therefore those two right triangles can go into each other according to side angle side rule. And from the fact that those two right triangles can go into each other, we will derive that OQ of the right triangle AOQ equals to QM of the right triangle OQM. We derive that AQ equals to QM. AQ equals to QM according to the rule that corresponding sides in congruent triangles are equal to each other. Those two triangles can go into each other, therefore the two corresponding sides, that is to say AQ and QM, must be also equal to each other in their lengths. So if you found out that AQ equals to QM. So if you relate to the big associated triangle AQM, AQM is an associated triangle because AQ equals to QM. So in the big associated triangle AQM, in front of those two equal sides, we have those two angles that must be also equal to each other in their sizes. So if we define the size of this angle as beta, then the size of this angle must be also equal to beta because they are equal to each other. So in the next step, I'll present to you a new rule, and we will implement the new rule in our drawing. The new rule is rule 8. According to rule 8, an external angle of a triangle is equal to the sum of the two interangles that are not adjacent to it. I repeat again. According to rule 8, an external angle of a triangle is equal to the sum of the two interangles that are not adjacent to it. So in the drawing you have triangle ABC that could be any triangle. Those three angles alpha, beta, and gamma are defined as interangles because they are located inside triangle ABC. While this is angle ACF that is defined by E. Angle E is defined as an external angle because it is located outside triangle ABC. So what is the size of the external angle E? According to this rule 8, the size of the external angle E is equal to the sum of the two interangles that are not adjacent to it. This is the internal angle gamma that is definitely adjacent to angle E. The two other interangles that are not adjacent to it are those two angles alpha and beta. And therefore, according to rule 8, the size of the external angle E is equal to alpha plus beta. Those two angles are the two interangles that are not adjacent to angle E. So angle E equals to alpha plus beta. The external angle E equals to alpha plus beta according to rule 8. So we can implement rule 8 in our drawing. Why? Because in our drawing, if we relate to the big associated triangle AQM, those three angles are all defined as interangles because they are located inside the associated triangle AQM, while this is angle AQP that is defined as an external because it is located outside triangle AQM. So what is the size of the external angle AQP? According to rule 8, the size of the external angle AQP must be equal to the sum of the two interangles that are not adjacent to it. This is angle AQM that is definitely adjacent to angle AQP. The two other interangles that are not adjacent to this angle AQP are those two angles. And therefore, the size of the external angle AQP according to rule 8 must be equal to beta plus beta. And again, the size of this external angle AQP according to rule 8 is equal to the sum of the two interangles that are not adjacent to it. That is to say, it is beta plus beta. Beta plus beta is 2 beta. So the size of the external angle AQP is equal to 2 beta. But we have already found out that the size of the external angle AQP is 45 degrees. So we can substitute angle AQP by 45 degrees. So 45 degrees equals to 2 beta. Here we divide this equation by 2 and finally get that the size of the that angle beta equals to 45 degrees over 2, that is 22.5 degrees in its size. So actually, this is angle beta. The size of this angle beta is 22.5 degrees. This is also angle beta. Is equal to 22.5 degrees in its size. In the next step, we will focus on the right lower triangle OQM. In the right lower triangle OQM, the sum of the angles must be equal to 180 degrees according to the rule that the sum of the angles in any triangle is equal to 180 degrees. So which angles we have in the right lower triangle OQM? We have this angle that is 90 degrees plus this angle beta that is 22.5 degrees plus this missing angle OQM. In total, the sum of those three angles must be equal to 180 degrees. Repeat again, this right lower triangle OQM (90 degrees plus 22.5 degrees) plus the size of the missing angle missing angle OQM, in total it must be equal to 180 degrees. Here we subtract 90 degrees from this equation, and we get that 22.5 degrees plus the size of the missing angle OQM. In total, it must be equal to 180 degrees minus 90 degrees is 90 degrees. So if you found out that 22.5 degrees plus angle OQM, in total, it must be equal to 90 degrees. Here we subtract 22.5 degrees from the equation, and we get that the size of the missing angle OQM is equal to 90 degrees minus 22.5 degrees is 67.5 degrees. So if you found out that the size of this missing angle OQM is equal to 67.5 degrees. We have the rule that says that vertex angles are equal to each other. Repeat again. We have the rule that says that vertex angles are equal to each other. Those two angles, alpha and beta, are defined as vertex angles, and they are equal to each other and their sizes. So again, alpha equals to angle beta. Likewise, another pair of vertex angles are those two angles. We define this angle as 1 and this angle as 2. Again, those two angles, 1 and 2, are also defined as vertex angles, and they are equal to each other in their sizes. That is to say, angle 1 equals to angle 2. So we can implement the rule in our drawing. Because in our drawing, those two angles are also defined as vertex angles. Those two angles are also defined as vertex angles, and they are equal to each other in their sizes. So angle x equals to 67.5 degrees in size. Angle x equals to 67.5 degrees in size. And that is the answer to the question. And again, I should found out that the size of the missing angle PQB is equal to x is equal to 67.5 degrees in its size. So we finished with the first question. In the next step, I'll present to you the second question, and we'll solve the second question of this lecture. In the second question, our task is to find out the area of this given shape. So, in the drawing, we have a semicircle. PQ is the diameter of this semicircle that is equals to 10 units in itself. If the diameter PQ equals to 10, then the radius must be equal to 5. So the radius of this semicircle equals to 5 units in its length. Write it down. In addition, you know that inside this big semicircle we have the big square BCD and the small square MEFC. Again, our task is to find out the area of this given shape. So first of all, we'll define the center of this semicircle. This point is point O. And we'll join points O and A together by a straight line. Point O is the center of the semicircle, point A is the point on the semicircle itself, therefore OA is the radius of this semicircle that is equals to 5 units in its length. The radius of the semicircle equals to 5 units. ABCD is a square, and therefore this angle must be equal to 90 degrees in its size, according to the rule that all the angles inside any square are right angles. Likewise, MEFC is also a square, and therefore this angle must be equal to 90 degrees in its size. In the next step, we join points O and E together by straight line. OE is of course the radius of this semicircle that is equal to 5 units in its length. So in the next step, we define the length of one side of the big square ABCD as A. So AB equals to BC equals to CD equals to BA equals to DA equals to A. AB equals to A according to our definition. We define the length of the short line segment OC as X. So what is the length of the short line segment BO? On the drawing it is very easy to see that BO equals to BC minus OC. So write it down. BO equals to BC minus OC. So BO equals to BC. BC is A minus OC. OC is X. So in total, we found out that BO equals to A minus X units in its length. In the next step, we define the length of one side of the small square MEFC as B. So EF equals to B, CF equals to B, MC equals to B, and ME also equals to B. In the next step, I'll copy the right triangle ABO in a new page, and we will implement on this right triangle ABO the Pythagoras theorem. According to the Pythagoras theorem, in any right triangle, the square of the hypotenuse equals to the sum of the squares of the perpendiculars. Here by PT is a version for Pythagoras theorem. Side AB of the right triangle AB equals to A units in its length. The hypotenuse AO is also the radius of the semicircle that is equals to 5 units in its length. And BO equals to A minus X units in its length. So actually, this is the right triangle ABO that is coming from the original drawing. According to the Pythagoras theorem, in this right triangle ABO, AO squared, that is the square of the hypotenuse, equals to AB squared plus BO squared. So I will write it down. This will be equation 1. Only to equation 1. AO squared, that is the square of the hypotenuse, equals to AB squared plus BO squared. The hypotenuse AO equals to 5 units in its length, therefore AO squared is 5 squared, that is 25. And this is equal to AB squared. AB is A, therefore AB squared is A squared plus BO squared. BO equals to A minus X, therefore BO squared equals to A minus X squared. So in total, according to equation 1, we actually found out that 25 equals to A squared plus A minus X squared. Likewise, I copy this right triangle OEF in a new page, and we will implement on it the Pythagoras theorem. Here by PT is a version for Pythagoras theorem. The hypotenuse O equals to 5 units in itself. It is also the radius of the semicircle. EF equals to B, and side OF on the other line OEF, in total OF equals to X plus B. Okay. This is the right triangle OEF, that is a copy from the original drawing. In this right triangle OEF, according to the Pythagoras theorem, OE squared, that is the square of the hypotenuse, equals to EF squared plus FO squared. So I write it down. This will be equation 2. According to equation 2, OE squared, that is the square of the hypotenuse, equals to EF squared plus OF squared. OE is 5, therefore OE squared is 5 squared, that is 25. And it is equals to EF squared. EF is B, therefore EF squared is B squared plus OF squared. OF is X plus B, therefore OF squared is X plus B squared. So in total, according to equation 2, we found out that 25 equals to B squared plus X plus B squared. This is according to equation 2. Well, according to equation 1, we already found out that 25 equals to A squared plus A minus X squared. So in the next step, we get equation 3 that says that 25 according to equation 1 must be equal to 25 according to equation 2. So according to equation 3, 25 according to equation 1 must be equal to 25 according to equation 2. Twenty-five according to equation 1 equals to A squared plus A minus X squared. And this is equal to 25 according to equation 2. 25 according to equation 2 equals to B squared plus X plus B squared. So here we'll open the brackets on both sides of this equation, equation 3, and finally get that according to equation 3, A squared plus A minus X squared. A minus X squared equals to A squared plus X squared minus 2 times A times X, and it is equals to B squared plus X plus B squared. X plus B squared equals to X squared plus B squared plus 2 times X times B. So here we have X squared on both sides of this equation, so X squared we get cancelled. Also we cancelled X squared. In this side of equation 3 we left with A squared plus A squared, that is 2A squared minus 2AX. While on the other side of this equation 3 we left with B squared plus B squared, that is 2B squared plus 2bx. So here we divide this equation, equation 3 by 2, and finally get that according to equation 3, 2a squared over 2 is a squared, minus 2ax over 2 is minus ax, and it is equals to 2b squared over 2 is b squared, and 2bx over 2 is bx. So total, according to equation 3, we actually found out that a squared minus ax equals to b squared plus bx. Here we add ax to this equation, equation 3, and finally get that according to equation 3, a squared equals to ax plus bx plus b squared. So here we subtract from this equation 3 b squared. We get that according to equation 3, a squared minus b squared equals to, here we have ax plus bx. We take x as a second factor from those two expressions, so inside the brackets we left with a plus b. So total according to equation 3, found out actually that a squared minus b squared equals to x times a plus b. We have the famous algebraic identity that says that a squared minus b squared equals to a plus b times a minus b. And it equals to x times a plus b. A is the length of one side of the big square, and b is the length of one side of the small square. A is a length, it is absolutely straight line. So a and b as a length are absolutely a positive number. Again, a and b are lengths, and therefore they are positive numbers. And you add two positive numbers to each other, the result must be a positive number. So a plus b must be a positive number, and therefore it is allowable to divide this equation 3 by a plus b. Because it can never be equal to 0, it must be a positive number. So we divide this equation 3 by a plus b. So here a plus b will get cancelled, and we have to only with a minus b. Here a plus b also will get cancelled, and we have to only with x. So in total, according to equation 3, we found out that a minus b equals 2x. Here we will add b to this equation 3, and get that according to equation 3, a equals to x plus b. So here we subtract x from this equation 3, and get that according to equation 3, a minus x equals to b. So here we will square both sides of this equation 3, and we get that according to equation 3, a minus x squared equals to b squared. And again, according to equation 3, we should find out that a minus x squared equals to b squared. Our test is to find out the area of this green shape. So what is the area of the green shape? From the drawing, it is very easy to see that the area of the green shape equals to the area of the big semicircle minus the area of the big square ABCD minus the area of the small square MEFC. Repeat again, actually found out that the area that we are looking for this question, that is the area of this green shape, is equal to the area of the big semicircle minus the area of the big square minus the area of the small square. The area of the semicircle equals to the area of the circle over 2. That is to say, it is equals to pi r square over 2. but we already found out that the radius r of this circle is 5. So r squared is 5 squared, that is 25. So pi r squared is 25, pi r squared over 2 is 25 pi over 2. In total, we found out that the area of the big semicircle, the area of this big semicircle equals to 25 pi over 2 square units in its size, minus the area of the big square ABCD. One side of square ABCD is A, therefore the area must be equal to A squared, so it is minus A squared. One side, the area of one side of the small square is B, therefore the area of the small square must be equal to B squared, so it is minus B squared. So in total, if we found out that the area of the green shape equals to the area of the semicircle, that is 25 pi over 2, minus the area of the big square, that is A squared, minus the area of the small square, that is B squared, minus B squared. So the area of the green shape in total equals to 25 pi over 2. Here we take minus 1 as a common factor from those two expressions, so inside the brackets we left only with A squared plus B squared. So in total, we found out that the area of the green shape equals to 25 pi over 2 minus A squared plus B squared. According to equation 1, we have only found out that 25 equals to A squared plus A minus X squared. And again, according to equation 1, we only found out that 25 equals to A squared plus A minus X squared. And according to equation 3, we actually found out that A minus X squared equals to B squared. According to equation 3, we only found out that A minus X squared equals to B squared. Therefore, we can substitute A minus X squared in this equation 1 by B squared from equation 3. We do it again. We substitute A minus X squared in this equation 1 by B squared from equation 3. And we get that according to equation 1, 25 equals to A squared plus A minus X squared. But A minus X squared according to equation 3 is B squared. So it is plus B squared. So in total, according to equation 1, we actually found out that A squared plus B squared equals to 25. And therefore, we can substitute A squared plus B squared here by 25. We do it now, and we get that the area of the green shape in total equals to 25 pi over 2 minus A squared plus B squared. And A squared plus B squared according to equation 1 is 25. So it is minus 25. So in total, we found out that the area of the green shape, in total it is equal to either 25 pi over 2 minus 25 square units in its size. In terms of numbers, the value of this expression is equal to 14.27 square units in its size. Then again, we found out that the area that we are looking for in this question, that is the area of this green shape, it is equal to either 25 pi over 2 minus 25 square units. So in terms of numbers, the area of this green shape equals to 14.27 square units in its size. So we finish with the second question. In the next step, I will summarize the lecture. We'll start with the first question, of course. In the first question, our task is to find out the size of this angle x, or the size of angle PQB is equal to x. We have to find out the value of angle x. So in the domain, we have a quarter circle. A or B is a quarter circle. this is angle AOB, this is a right angle. This is angle APQ, that is also a right angle. We also know that AP equals to PQ. Again, our test is to find out the size of angle PQ is equals to x. We have to find out the value of angle x. So first of all, we completed the quarter circle to a semicircle. Again, we completed the quarter circle to a semicircle. We define this point as point M. So actually, AM is the diameter of the semicircle according to our construction. Repeat again, AM is the diameter of the semicircle according to our construction. So AM is the diameter, it is absolutely a straight line. So if we focus on the right side of the straight line AM point O, here the sum of the angles must be equal to 180 degrees according to Rule 3. Rule 3 says that the sum of the angles on one side of a straight line is equal to 180 degrees. So which angles we have at the right side of AM at point O? We have this angle that is a right angle, plus this missing angle. In total, the sum of those two angles must be equal to 180 degrees according to Rule 3. Therefore, this missing angle must be equal to 90 degrees in its size. In the next step, I extended the line segment PQ by straight line until it touches the semicircle. But the question is where the extended line segment PQ will touch the semicircle. We assume that the extended line segment PQ will touch the semicircle at this point, point L. And therefore, according to our assumption, we have peripheral angle APL that is equal to 90 degrees in its size according to what is given as the equation, and peripheral angle APL subtend on a chord AL. Again, peripheral angle APL definitely subtend on chord AL. But the problem is that AL cannot be the diameter of the semicircle. Why? Because AL doesn't pass through point O, that is the diameter of the, and that is the center of the semicircle, and we know that only chord that passes through the center of the circle can be the diameter of the semicircle. Therefore, AL is not the diameter of the semicircle. Therefore, we have here contradiction to Rule 5. Why? Because according to Rule 5, any peripheral angle that is equal to 90 degrees in size must subtend on the diameter of the semicircle. So here peripheral angle APL equals to 90 degrees in size according to what is given as the equation, and still it doesn't subtend on the diameter of the semicircle, because AL is definitely not the diameter of the semicircle. So due to the contradiction to Rule 5, we must conclude that the extended line segment PQ doesn't touch the semicircle at this point, point L. So in the next step, we will assume that the extended line segment PQ will touch the semicircle at this point, point H. Therefore, according to our assumption, we have peripheral angle APH. Peripheral angle APH equals to 90 degrees in size according to what is given as the equation, and peripheral angle APH subtend on chord AL. On chord AH. Again, peripheral angle APH subtend on chord AH. Again, we have contradiction to Rule 5 because AH is definitely not the diameter of the semicircle. Why? Because AH doesn't pass through the center of the semicircle, that is point O, and therefore AH cannot be the diameter of the semicircle. But according to Rule 5, because of the fact that the peripheral angle APH equals to 90 degrees in its size according to what is given in the equation, it must subtend on the diameter of the semicircle, but it subtend on AH that is not the diameter of the semicircle. So due to the contradiction to Rule 5, we must conclude that the extended line segment PQ will not touch the circle at point H. So therefore, we must conclude that the extended line segment PQ will touch the semicircle at point M and not in any other point. Otherwise we will have contradiction to Rule 5. Now we have peripheral angle APM that equals to 90 degrees in size, and it is subtend on AM, that is the diameter of this semicircle, is exactly according to Rule 5. So in the next step, we actually join points A and Q together by straight line. By joining points A and Q, we created the right and associated triangle, triangle APQ. We have the rule that says that in front of equal sides in the triangle there are equal angles. So if we relate to the right and associated triangle, triangle APQ, in front of those two equal sides, we have those two angles that must be also equal to each other in their sizes. So if the size of this angle is alpha, then the size of this angle must be also equal to alpha because they are equal to each other. And we know that the sum of the angles in any triangle is equal to 180 degrees. It is true in any triangle, and therefore it is true in the right and associated triangle, triangle APQ. So which angles we have in the right and associated triangle, triangle APQ? We have 90 degrees. Alpha plus alpha is 2 alpha, so 90 degrees plus 2 alpha equals to 180 degrees. So here we subtract 90 degrees from this equation, and found out that 180 degrees minus 90 degrees is 90 degrees. So 2 alpha equals to 90 degrees. Here we divided this equation by 2 and found out that alpha, the missing angle alpha equals to 90 degrees over 2. So 90 degrees over 2 is 45 degrees. So this is the missing angle alpha, this equals to 45 degrees inside, and this is also the missing angle alpha, this is equals to 45 degrees in size. In the next step, we prove that those two right triangles can go into each other according to side angle side rule. That is to say, we prove that the right upper triangle AQO can go into the right lower triangle OQM according to side angle side rule. So why those two right triangles can go into each other? First of all, AO equals to OM. They are both the area of the semicircle, therefore they are equal to each other. In addition, those two angles are both right angles, therefore they are equal to each other. And finally, OQ is the common side that belongs to both triangles, so we can write down that OQ equals to itself is the common side that belongs to both triangles. So we found out in total that those two right triangles can go into each other according to side angle side rule. Repeat again. We found out that the upper right triangle AOQ can go in, this is the side can go to the right lower triangle OQM according to side angle side rule. That is to say, we prove that those two sides and the angle that is included between those two sides of the right triangle AOQ are corresponding equal to those two sides and the angle that is included between those two sides in the right triangle OQM. And therefore, those two right triangles can go into each other according to side angle side rule. And from the fact that those two right triangles can go into each other, we know that side AQ of the right triangle OQM is equal to side QM of the right triangle OQM. And again, we know that AQ equals to QM according to the rule that corresponding sides and can go into triangles are equal to each other. Those two triangles can go into each other, therefore the two corresponding sides, that is to say AQ and QM, must be also equal to each other in their lengths. So AQ equals to QM. AQ equals to QM, and if we relate to the big associated triangle AQM, we have the rule that in front of equal sides there are equal angles. So in front of those two equal sides, we have those two angles that must be also equal to each other and their sizes. So if we define the size of this angle as beta, then the size of this angle must be also equal to beta because they are equal to each other. In the next step, I presented to you a new rule, and we implemented the new rule in our drawing. The new rule is rule 8. So I repeat rule 8. According to rule 8, an exterior angle of a triangle is equal to the sum of the two interior angles that are not adjacent to it. This is triangle ABC, that could be any triangle. In this triangle ABC, those three angles alpha, beta, and gamma are defined as interior angles because they are located inside triangle ABC. While this is angle ACF, this is equal to E according to our definition. Angle E is defined as an exterior angle because it is located outside triangle ABC. So what is the size of the exterior angle E? The size of the exterior angle E, according to this rule, rule 8, is equal to the sum of the two interior angles that are not adjacent to it. This is the interior angle gamma. It is definitely adjacent to angle E. The two other angles that are not adjacent to angle E are those two interior angles. Therefore, we have found out that according to rule 8, the size of angle E is equal to alpha plus beta, that the sum of the two interior angles that are not adjacent to it. Angle E equals to alpha plus beta. So we can implement rule 8 in our drawing. If we focus on the big associated triangle AQM, those three angles are defined as interior angles because they are located inside triangle AQM, while this is angle AQP that is located outside triangle AQM, therefore it is defined as an exterior angle. The size of the exterior angle AQP according to rule 8 equals to the sum of the two interior angles that are not adjacent to it. This is angle AQM that is definitely adjacent to angle AQP. The two other angles that are not adjacent to it are those two angles, beta and beta. And therefore, according to rule 8, the size of the external angle AQP must be equal to beta plus beta, that is 2 beta. And again, if we relate to the big associated triangle AQM, according to rule 8, the size of the external AQP equals to the sum of the two integrals that are not adjacent to it. Which is, to say it is beta plus beta, this is 2 beta. Again, the size of this external AQP is equals to the sum of the two integrals that are not adjacent to it. Which is to say it is beta plus beta, this is 2 beta. But we already found out that the size of the external AQP is 45 degrees. So we can substitute angle AQP by 45 degrees. And get that 45 degrees equals to 2 beta. Here we divided this equation by 2 and finally found out that beta equals to 45 degrees over 2, that is 22.5 degrees. So this is the missing angle beta, that is equal to 22.5 degrees in size, and this is also angle beta, that is equal to 22.5 degrees in its size. In the next step, we use the rule that works actually we focus on the right lower triangle OQM. In the right lower triangle OQM, the sum of the angles must be equal to 180 degrees. So which angles we have in the right lower triangle OQM? We have this angle that is the right angle, plus this angle beta that is 22.5 degrees in size, plus this missing angle OQM, in total they must be equal to 180 degrees. And again, the right lower triangle OQM, 90 degrees plus 22.5 degrees, plus the size of the missing angle OQM, in total must be equal to 180 degrees. Here we subtracted 90 degrees from this equation, and we found out that 180 degrees plus 90 degrees is 90 degrees, so 22.5 degrees plus the size of the missing angle OQM, in total must be equal to 90 degrees. Here we subtracted 22.5 degrees from this equation, and we found out that the size of the missing OQM equals to 90 degrees minus 22.5 degrees is 67.5 degrees. So she found out that the size of this missing angle OQM is equal to 67.5 degrees. In the next step, we use the rule that says that vertex angles are equal to each other. And again, we use the rule that says that vertex angles are equal to each other. In the drawing, we have those two angles alpha and beta that are defined as vertex angles, and they are equal to each other in their sizes. That is to say, alpha equals to beta. Likewise, those two angles are also defined as vertex angles, and they are equal to each other in their sizes. That is to say, angle 1 equals to angle 2. So you can implement a new rule in our, it is not a new rule, you can implement the rule in our drawing. Why? Because in our drawing, we have those two vertex angles that must be equal to each other. That is to say, x equals to 67.5 degrees in size. So she found out that the angle that we are looking for in this question, that is angle x, is equal to 67.5 degrees in size. And then again, she found out that the missing angle PQV is equal to x, is equal to 67.5 degrees in its size. So we finish with the first question. In the next step, I present to you the second question, and we solve the second question of this lecture. In the second question, our task is to find out the area of this great shape. So in the drawing we have a semicircle. We know that the diameter PQ equals to 10, therefore the radius is 5. The radius of this semicircle equals to 5 units in its length. In addition, we know that inside this big semicircle we have the big square ABCD and the small square MECF. Again, our task is to find out the area of this great shape. So first of all, we define the center of this semicircle. This point is point O. We join points O and A together by side line. Point O is the center of the semicircle. Point A is the point on the semicircle itself. Therefore, OA is the radius of this semicircle. This is equal to 5 units in its length. Likewise, we join points O and E together by certain OE is also the of this semicircle that is equal to 5 units in its length. ABCD is a semicircle, therefore this circle must be equal to 90 degrees in its size. Likewise, MEFC is also a square, therefore this circle must be equal to 90 degrees in its size. We define the length of one side of the big square ABCD is A. So AB equals to BC equals to CD equals to DA equals to A. We define one side of this small square MEFC as B. So CM equals to ME equals to EF equals to FC equals to B. CF equals to B and EF also equals to B. So here we define the length of the short line segment OC as X. So what is the length of line segment BO? From the drawing it is very easy to see. From the drawing it is very easy to see that BO equals to BC minus OC. Again, BO equals to BC minus OC. So BO equals to BC minus OC. BO equals to BC, that is A, minus OC, that is X. So in total, BO equals to A minus X. In the next step, I copied the right triangle ABO in a new page and implemented the Pythagoras theorem on this right triangle ABO. According to the Pythagoras theorem, in any right triangle, the square of the hypotenuse equals to the sum of the squares of the perpendiculars. So actually, this is the right triangle ABO that I copied from the original domain. In this right triangle ABO, according to the Pythagoras theorem, AO squared, that is the square of the hypotenuse, equals to AB squared plus BO squared. AO is 5, therefore AO squared is 5 squared, that is 25. And it is equal to AB square. AB is A, therefore AB square is A square plus BO square. BO is A minus X, therefore BO square is A minus X square. So in total, according to equation 1, we found out that 25 equals to A square plus A minus X square. Likewise, I copied the right triangle OEF in a new page and we implemented the Pythagoras theorem on this right triangle OEF. This is the right triangle OEF that I copied from the original domain. The hypotenuse OE equals to 5 units in itself, EF equals to B units in itself, and OF in total equals to X plus B. OF equals to X plus B. So in this right triangle OEF, according to the Pythagoras theorem, OE squared, that is the square of the hypotenuse, equals to EF squared plus OF squared. OE is 5, therefore OE squared is 5 squared, that is 25, and it is equals to EF squared. EF is B, therefore EF squared is B squared plus OF square. OF is X plus B, therefore OF square is X plus B square. So in total, according to equation 2, we found out that 25 equals to B square plus X plus B square. This is according to equation 2, while according to equation 1, we have already found out that 25 equals to A square plus A minus X square. Therefore, we created equation 3 that says that 25 according to equation 1 must be equal to 25 according to equation 2. Then again, we created equation 3 that states that 25 according to equation 1 must be equal to 25 according to equation 2. 25 according to equation 1 equals to A square plus A minus X square. And it must be equal to 25 according to equation 2. 25 according to equation 2 equals to B square plus X plus B square. So in total, according to equation 3, we found out that A square plus A minus X square equals to B square plus X plus B square. Here we open the brackets on both sides of this equation 3, and find out that according to equation 3, A square plus A minus X square. A minus X square equals to A square plus X square minus 2 times A times X. And it is equals to B square plus X plus B square. X plus B square equals to X square plus B square plus 2 times X times B. Here we have X square on both sides of this equation, so X square we will cancel. After we cancel X square, in this side of equation 3 we left only A square plus A square, that is 2A square minus 2AX. While in the other side of this equation 3, we left with B square plus B square, that is 2B square plus 2XB. So in total, according to equation 3, we found out that 2 times A square minus 2AX equals to 2B square plus 2XB. Here we divided this equation 3 by 2, and found out that 2A square over 2 is A square, minus 2AX over 2 is minus AX, and it is equals to 2B square over 2 is B square, and 2BX over 2 is BX. So in total, according to equation 3, we found out that A square minus AX equals to B square plus BX. Here we added x to this equation, equation 3, and found out that according to equation 3, a squared equals to ax plus bx plus b squared. Here we subtracted b squared from this equation, equation 3, and found out that according to equation 3, a squared minus b squared equals to, here we have ax plus bx. So we took x, the second factor from those two expressions, so inside the brackets we left only a with a plus b. So according to equation 3, we found out that a squared minus b squared equals to x times a plus b. Here we have the famous algebraic identity that states that a squared minus b squared equals to a plus b times a minus b, and it is equals to x times a plus b. A and b are the lengths of the big square and the small square, and therefore they are positive numbers, and when you add two positive numbers with each other, the result must be a positive number. Therefore, a plus b must be a positive number, and therefore it is allowable to divide this equation 3 by a plus b. It can never be equal to 0, it must be a positive number. So we divided this equation 3 by a plus b. Here a plus b will get cancelled, we left only with a minus b. Here also a plus b will get cancelled, we left only with x. And total according to equation 3, we have found out that a minus b equals to x. Here we added b to this equation, and found out that a equals to x plus b. Here we subtracted x from this equation, and finally found out that a minus x equals to b. Here we squared both sides of this equation, and finally found out that a minus x squared equals to b squared. According to equation 3, a minus x squared equals to b squared. Our task is to find out the area of this green shape. So what is the area of the green shape? From the drawing it is very easy to see that the area of the green shape equals to the area of the big semicircle minus the area of the big square ABCD minus the area of the small square MEFC. Repeat again, the area of the green shape equals to the area of the semicircle minus the area of the big square minus the area of the small square. The area of the semicircle equals to the area of the circle over 2. That is to say it is pi r square over 2. R is 5, so pi r square over 2 is 25 pi over 2. Minus the area of the big square. One side of this square is equals to a unit, and therefore the area of the big square must be equal to a square, so it is minus a square. Minus the area of the small square. One side of the small square equals to b units in itself, and therefore the area of the small circle to the area of the small square must be equal to b square, so it is minus b square. So in total we found out that the area of the green shape equals to 25 pi over 2 minus a square minus b square. So it is 25 pi over 2, and we took minus 1 second factor from those two expressions, so inside the brackets we left with a square plus b square. So in total we actually found out that the area of the green shape equals to 25 pi over 2 minus a square plus b square. According to equation 1, we only found out that 25 equals to a square plus a minus x square. This is according to equation 1. When according to equation 3, we only found out that a minus x square equals to b square. Here a minus x square equals to b square. So therefore, we can substitute a minus x square in this equation 1 by b square from equation 3. We did it, and we found out that according to equation 1, 25 equals to a square, and a minus x square is b square, according to equation 1. So in total, we found out that 25 equals to a square plus b square. So we can substitute a square plus b square by 25 from equation 1. We did it, and we actually found out that the area of the green shape in total equals to 25 pi over 2 minus a square plus b square, that is 25 according to equation 2. Therefore, 25 pi over 2 minus a square plus b square is 25 pi over 2 minus 25, because a square plus b square is 25. So in total, we found out that the area of the green shape equals to either 25 pi over 2 minus 25 square units in its size. So in terms of numbers, the value of this expression is equal to 14.27 square units in its size. Okay? Thank you very much.